Hello and welcome to the final week of C++ 101. So this is week 8. I'll be here and so will Gavin.
Hello.
Alright, so like I said, today's the last day. We're going to be... Yeah, boo. We're going to be covering some odds and ends with object-oriented programming, and we're going to be... The kinds of things that we're going to be delving much deeper into 102, but these concepts are very important to understand. I want to introduce them early. So, as I said in the last video, last class, I kind of did trick people into working in an object-oriented manner with the homework, where people were carrying around these structures with state in them and had these methods or functions, but they were they behaved like methods that took in the state as a pointer. And then last week we talked about how we can sort of condense that syntax using what are called classes. And classes are a way to facilitate object-oriented programming. They're not a requirement for working with object-oriented programming, because object-oriented programming is a paradigm and not any specific set of technology. But classes are a very common mechanism to express object-oriented design. However, classes do give us some really cool features beyond just shortening the code that we previously had to write. They give us some very unique and very powerful ideas that we can represent. So,
by the way, things can't be very unique. They're unique or they're not unique. It's that simple.
Partially.
I may have mentioned that before.
I think you did.
Several hundred times. Yes. Go on, Visual Studio, you can do it.
All right, I'm going to go ahead and type out some code. I want auto properties and resharper.
And C# syntax.
Yeah. Okay, so what we have here is we have this nice little product class.
Lovely.
I really do love the sounds that my keyboard makes. Okay, so yeah, we have a product class, and that's great. Any questions about the product class, because we covered this stuff last week, and understanding this syntax is going to be a prerequisite to understanding this week, and we have more than enough time to go over anything if people are struggling with these concepts.
Oh yes, Dispally product.
Dispally. I thought we established that I can make up any word I want.
No.
No?
No. Just no.
Well, fine.
Not
then.
until you learn the ones that are already in existence.
I want to inherit from the English dictionary. Anyway,
Or at least implemented.
yes.
Then you could implement foreign. Anyway.
Okay, so I guess there's no questions about this code, because we're not getting any questions about this code, so I'll assume that there are none.
Your deductive reasoning is positively Sherlockian.
Sherlocking?
Sherlockian.
Sherlockian.
I should probably have said Holmesian, but I was running fast towards the end of the sentence without any idea how it was going to finish.
Huh.
Yes, in the manner of Sherlockian.
Okay, so we have a product, and this is very simple. Basically, you can conceptualize this as a structure containing a string and a double, a variety of methods that allow us to work on that structure in a very nice, concise, and clean manner. But that's not the last most important thing we can do with classes. One of the most powerful concepts of classes in C++ is called inheritance. The idea of inheritance extends to a lot of different concepts in object-oriented design in the context of C++. And that's why I just prefaced this entire discussion with saying that, is that inheritance in C++ is how you express both true inheritance and interface implementation. Now, it's okay if you don't understand what those words are, but if you do, if you're coming from C# or Java, it might seem confusing how I'll use the word inheritance to describe the implementation of interfaces, but inheritance is the mechanism in which we do that. However, we're going to be talking about inheritance at a very basic level starting off. We're going to be talking about the basic idea of we have this awesome class product that has some truly amazing and powerful code within it. But we want something more. We want a special product. We want a product, sure, but we want something in addition to this product. We want to add additional functionality to it without disturbing the actual product class definition and without disturbing any of the other code that may depend on the actual product definition. So we do this with inheritance. Special product inherits from product. We know this because immediately after the identifier for the class, we have a colon, followed by the keyword public, followed by the identifier product. I do want to point this out really quickly. You'll notice that there is this access modifier-y thing inside of our inheritance definition, our list of classes that we inherit from, and take it for granted now. In C++, there's such a thing as private inheritance, which sadly is the default, because C++ has a tendency to force you to annotate your code under the normal circumstances and not the edge cases. You will most commonly be using public inheritance. You will very rarely use private inheritance, and we're not going to be discussing private inheritance this week. We'll cover it more in 103, but it really lacks very many uses. So
it's one of those areas where you're going to be less confused if you knew nothing coming in than you are if you know C# or any other language where the idea of private inheritance is silly.
Non-existent.
And silly.
Yeah, well, it is silly. And it's non-existent in every other language I've ever heard of. But yeah. So public inheritance, that's what we're going to be using, and that's what you should use, and you need that public modifier right there. Otherwise, your code will not work in very well-defined ways. You'll get some nasty C++-esque compiler errors, which will be very confusing. So just like how you always need to terminate a class definition with a semicolon, you must always annotate your inheritance with the keyword of public.
Actually, is it possible to show those errors? Just to give some, so that when you see those errors, you can go,
Yeah.
Show us a mistake, Nelson.
So this will work. We can use our special product. But if we take this modifier off, this will also kind of work, but we won't get any amount of, as you'll see, if I try to access product.displayProduct, you'll notice we get a nice little error. It says product display product is not accessible because special product uses private to inherit from product. Actually, that's not that bad at all, to be honest.
It's got relevant sounding words.
Yeah. If you ever see stuff like that, you just need to know that you need to use public inheritance. But what does inheritance really provide us with? Well, inheritance provides us with the idea of having special product also be a product, in the sense that it carries along with it fields, methods, and other members. There's actually a lot of rules involving destructors and constructors that we're not going to be talking about until 102. But it carries with it everything else. We've essentially, although this isn't technically the case, and there's a lot of additional points to make about what I'm about to say, but you can imagine that we literally took the definition of class product, which is, again, provided to us between lines 7 and 20, and we pasted it right into the definition of special product, which means that a special product will have all of the members Special product will have all of the members as product. Notice how these two lines of code work just fine, because all of the members are indeed available. Okay, so let's go ahead and talk about quickly being able to add functionality to special product. How do we add additional functionality to it? Well, adding functionality is actually very easy. I've added a method called ble, and now I can invoke ble. Like on line 34. This method is invocable. That will invoke the method defined on line 26. Product does not get a ble. Product doesn't get that member, only special products do. So now a special product is everything that a product is plus an additional method, which is a nice little feature. So let's talk about...
I was just going to say, the way one of the best ways to visualize it is that I think about this more with implementation, but it's the same thing. It's like a SNES or something, any old-fashioned cartridge-based gaming machine. The normal product class slots into the special product and brings all its functionality with it, and the special product has got that. But anything that you put on the special product obviously doesn't, that stays on the special product.
Yep.
Just words.
You're annotating a type. Okay, so let's talk about accessibility, because last week I kind of avoided talking about a special accessibility modifier that's going to play a very important role in inheritance. You'll notice that if I wanted to add a method to my special product called, let's say I wanted to add a method called display special product. And my display special product says special product name costs price. And let's say I made this example a little bit more interesting by adding an additional member. Let's say int count in stock, and then we have a void set stock int new stock count in stock equals new stock, and then I could say void int get stock return count in stock, and then I can add my display special product and say it costs this price, and there are count in stock in stock. And now my special product, I'm going to go ahead and say special.setStock 20, and then special.display special product. But you'll notice we get a nice little compiler error. We get an error saying that product name cannot access private member declared in product. This should bring back memories about the definition of what private is. Remember, private is the default accessibility in classes, meaning both string name and double price are private fields. They're private members. Private means that only within this class and this class alone can these members be accessed. That extends to children of the type. So there's one last accessibility modifier that I want to talk about, the last one that you will ever use, called protected. What is protected? Protected accessibility is private accessibility and accessibility from children. So by saying protected, nobody outside of product or any of its derivative types may access these two members, but it's more inclusive than private because derivatives of the type can access these members. So as you notice, when I hit F5, we'll get a appropriately compiling program saying special product 1 costs $23 and there are 20 in stock.
So any questions about any of this so far?
Yeah, how's everybody feeling about protected, about basic inheritance?
There is one question up there.
I don't understand. Now, how would you also define ble as void special product ble? I'm not sure what you mean.
That's not what it says. It says, now could you also define ble as void special product ble?
I still don't understand.
Well, instead of just define, could you define it longhand like that?
So you mean doing...
No, you made a method called ble.
Yeah, that's well, yeah, and this I deleted it, but...
Oh, well, it was still existing when he asked that question.
Oh, well, I think this is what he was
referred
asking,
to.
and the answer is yes. You do these implementations the exact same way. There's no difference. Can the child class use the same field names? Well, that's a good question. Accessibility is only going to come into play when there's a conflict. So if I tried to do a string name, we get what's referred to as a hidden member. And to access specific members, so you'll notice when I hit F5, we'll get special product blank costs 23 and there are 20 in stock. The reason we're getting blank is when the setName method is invoked, product name is set. When the display special product method is invoked, this name gets set. And that's because these conflict in their levels of accessibility. And as a result, we get the concept of what's called hiding. If I really wanted to confuse my field names, which you really shouldn't do, but if I really wanted to do that, what I could do on line 38 here is say product : name, which you'll notice works now because both setName on line 13 and special product display special product on line 38 both access the same field. So the answer is yes, but you want to be careful not to, because that will cause problems with hiding, and problems with hiding become very confusing very quickly. The constructor and destructor methods are kind of out of scope. The way that they behave as far as inheritance actually does get fairly involved. So we're going to be mostly talking about inheritance and polymorphism here. Again, it's going to be a short class, but these concepts are so important that I don't want to derail them on some more strangeness of the language. But that's going to be definitely in 103. Base constructors are not fun. Anyway, so... Okay, so we have our basic inheritance hierarchy here. Some important things to understand about inheritance. I mean, at this point, I don't think anything is really terribly complex. We have two classes. We have one class that is another class, but with additional members. But there are some very interesting things we can do with inheritance. One of the most interesting things is the implicit conversion between child types and base types. When I say that, I mean I have a method. If I have a method called void do stuff with product that takes in a product, I can invoke this do stuff with product given a special. Because a special product is a product. That's one of the things you might hear commonly used, a very common term used when people are describing inheritance is inheritance represents an is a relationship, not a has a relationship. An is a relationship is when a class is another class. And has a relationship is when a class contains another class. I want to really quickly point out, however, that in programming, it's actually less common to use is-a relationships, or for have in words. It is not very often that is-a relationships are appropriate.
Well, I mean, it sounds like has-a relationships are composition.
Yes. And composition is typically one of going to ridiculously increase the amount of flexibility of a program when used over inheritance in certain situations. But just to point out the impedance mismatch between the real world and the object-oriented design world, because there truly is an impedance mismatch where you feel like these ideas should be expressed in code in a particular way because they exist in the world in a particular way, but that's not always true. One of the best examples I can think of anyway, is the square and rectangle example. Now in mathematics, a square is a rectangle. So you might be tempted to, if you wanted to represent a square, you might be tempted to inherit from a rectangle. But what you've in effect done is you've broken a very important principle of object-oriented design. Most importantly, the rectangle will have methods on it, such as set width and set height. A square doesn't need those methods. In addition, a square is always going to enforce the fact that the width equals the height, either implicitly by only providing methods for modifying the width and not the height, or less implicitly where you just have a bit of validation logic that checks to see if the width is equal to the height, otherwise throws an error. But the point is that you won't be able to use a square object in every scenario that you can use a rectangle. But that's what inheritance is all about. If you cannot use a derivative type in all the situations where you can use a base type, you should not be using inheritance, or you should think about your inheritance hierarchy differently. So as a result, you'll notice that this is indeed valid. A special product is very much a product, and it doesn't change anything that makes a product, and it doesn't alter the behavior of what is carried around with the product. Therefore, it is appropriate to be able to treat a special product as if it were a product. So what exactly would be a has-a if special product had a product as a field? I wouldn't represent special product, if I were to represent this model using composition over inheritance, I wouldn't represent special product as a type that has a product field. Instead, I would invert what a product is. I would compartmentalize the different capabilities of a product into objects that can be swapped out. So you would still have one class called product, and then you would have a variety of classes that represent the bits and pieces of the behavior of the product, and then at runtime you would piece together that object and get a product out of it that has all of its little innards replaced with whatever you feel is appropriate. However,
your display special there would be a prime candidate for that.
Yeah, it would.
Because it's infinitely preferable to have just to be able to call display on a product and then have it display but relevantly to itself.
Right, it would enumerate its components and have each component choose to add additional information to the display message, thus making the display method incredibly more flexible. But we haven't talked yet about the most important aspect to inheritance, and we're going to get to it. We're going to talk about interface implementation very shortly, and I feel that once we do, the idea of composition will make a lot more sense than it does now. Because right now, every time people see their first inheritance, they're like, oh, super stoked on using inheritance to save a bunch of typing, and they run into issues. But fortunately, the inheritance construct in C++ provides us more than just basic rudimentary representing has-a relationships. Okay. So I'm going to go ahead and delete this code. I'm going to put up something for people to go ahead and write out.
Cool.
So go ahead and hit participate if you want to participate. Okay, so what I want is for people to just do some basic typing out inheritance code. And we're going to be building upon this example throughout the discussion we're going to be having for the remainder of the class. Basically, I wanted everyone just to get the basics of this example down and coded so that they can follow along with some of the problems that we're going to experience and then the solutions to those problems. So I want a shape class and a circle class.
Are you going to, regarding the circle class, and stop me if this is if you've deliberately not mentioned this, but line 11, you need to find the area.
Yes. Oh, right.
Yeah.
Blah, 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 blah.
Oh, that's all right then. I didn't know if you deliberately left that out.
There's your pi constant, guys. Okay, so...
The reason for that being that it's buried somewhere.
Yeah, it's buried somewhere in many different places, and... yeah. Okay, and again, I just want people to go through the rote motions of typing out something with inheritance. Remember this syntax right here, and go ahead and put this up, and then even if this doesn't quite work the way you expect it to, hopefully it does start getting people to think about what the problems with this might be and how we can fix them, because that's what we're going to be spending the rest of the class on. So I'm going to go ahead and reset everybody's ready, the whole 1, 2, 3, 4, 5, 6, 7, 8, 9.
Do you want to get them to write a rectangle class as well?
I'm probably going to have them do that later, once we solve the problems that this has.
Fair enough.
Okay, I'm going to go ahead and we're back. So let's go ahead and code this out and see what I was going to be trying to get at. Now people will notice some oddities with this, because we really want a circle to say get corners. And how many, shape. We want a shape to have get corners, but how many corners does a shape have? Well, it doesn't really have any actually. But we still want that functionality represented in a shape, because a circle is a shape, and all shapes have corners. So as a result, we represent this with inheritance by giving the shape this getCorners method. Okay, so then we can also have a getArea method. What's the area of a shape? Well, again, we don't have enough information. We know a shape has an area, all shapes have an area, and all shapes have corners, but we don't really know what a shape is, because the point of our shape is to sort of define a common language between a variety of classes so that we can take advantage of the fact that in C++ there's implicit conversions between child types and base types. So now to implement the circle. How many corners does a circle have? None. What's the area of a circle? Well, in order to calculate the area of a circle, we need to know the radius. So we need to provide an int radius and a int getRadius and a void setRadius. So now we can implement the getArea method, which is simply going to be pi times radius. Okay, so now we have our circle and our shape. What does this code do? It does exactly what we want it to. Well, not exactly. Pi is an approximation, a very rough approximation at that, but it does what we need it to. It properly says 50. So that's really nice. I'm actually going to change the getArea to return a double, by the way. And radius is going to be a double as well. So now we get 50.24, a little bit more accurate. Okay. So let's say we have a method called void display shape. Given that our circle properly calculates our radius to, or our area to 50.24 and properly returns 0 as the corners, if I were to invoke display shape, given our circle, so notice how I was able to completely fail because I forgot to inherit from shape. So notice how we get an error on display shape because circle is not a shape as of yet. As a result, there's no suitable user-defined conversion from circle to shape. But I can solve that problem using inheritance. So now I pulled in the definition of a shape, so now a circle is a shape. Which the most important aspect of inheritance is now we can treat all circles as if they were shapes, and we can reuse large swaths of functionality written in our code that's written in terms of a base type, and we can reuse them in the context of a derived type. However, there's a non-obvious thing that's about to happen. When I hit F5, what's the output of the program?
Not segfault.
Yes. Think about it. What's the output of this program?
You know, at some point you're going to be talking about segmentation faults, and then they're going to be it's going to be the answer to a question. And I'm going to say not segfault, and it will be very confusing.
This shape has 0 corners and an area of 0.
But
we have hidden these members within the circle. These members are only accessible from within the circle, and they're only accessible when statically referencing a circle type. More importantly, the display shape type, even though this code compiles, we still don't know enough yet about inheritance and object-oriented programming yet to properly represent what's referred to in the programming world as polymorphism. So the fact is that the biggest benefit that inheritance gives us, and the biggest and the overarching theme of today's class, we're not going to be sitting here and working out some stupid examples that you typically find in books where it's like, ooh, a dog's an animal, a cat's an animal, and then people are like, well, how do I use inheritance to do something fun? And it's like, oh, well, we're not going to be talking about virtual members for a while. But the fact is that when it comes to inheritance in C++, the concept of polymorphism is the absolutely most ridiculously important concept. I've used the word concept quite a few times in this sentence, and the sentence is slowly starting to turn into a paragraph.
Close parentheses.
Yeah.
Comma.
Where was I? In inheritance, the polymorphism is the most important aspect to inheritance. Period. Full stop. And I really want people to walk away today with a basic sort of understanding, a basic sort of feeling for what polymorphism gives us. And what we have here is an attempt to use polymorphism, but it's incorrect for a variety of reasons.
Exclamation mark.
Are you going to punctuate all of my sentences?
Question mark? Yes.
Okay.
Ellipsis.
So we have a failed attempt at polymorphism here. We have this method, this function right here called display shape that takes in a shape, and we really want to reuse this functionality for every shape, not just circles, but also rectangles, and maybe even shapes that aren't defined yet and won't be defined until down the line. We really want to be able to polymorphically access the members within the parameter passed in. But there are two very big problems with the way the code is organized at the moment.
Hold on. Sorry, I'll stop doing that.
The way in which we pass in shape is a problem, and the fact that we don't tell the C++ compiler that we want this to be polymorphic type. Let's talk about the first problem.
Okay.
Well, let's draw the first problem, actually, because my Photoshop works now.
Oh, that's pretty. That's a much improved splash screen.
Yeah, it's kind of nice.
Well, given how long you have to look at it for in Photoshop. They should have, like, elevator music for loading it. That'd be awesome.
Same with Visual Studio. Visual Studio is worse.
Yeah.
Okay, so we have this display function. He takes in a shape. Now, we also have main that defines a circle. That defines a circle and invokes the display function. Let's talk about what the circle looks like on main stack frame. Remember, we're not dynamically allocating this memory. So the memory is allocated for circle inside of main. So what does the stack frame look like? Well, we have this circle thing, and it's actually 2 bits of data. It's the circle members, and it's the shape members. On the stack, this is what circle looks like. It's a circle and a shape. Now, if you remember, when we have a function that does not take in a pointer type, this does not take in a pointer type at all. This takes in a non-pointer or reference type. What happens is we get a copy. Circle gets copied to the stack frame of display. But it's a little bit more complicated than that when you talk about inheritance. Because there is implicit conversion between circle and shape. There is. I mean, I'm not lying. The code does compile. But the things that get copied out of the circle are just the shape members.
Well, that makes sense because, I mean, display only knows how to deal with a shape.
Yeah.
It doesn't know what a circle is. So anything that's there that, I mean, what's it supposed to, how wide? See, this is catching. Something wrong. How is it supposed, it can't make any decision about what it should do with things that aren't part of a shape, are part of the circle.
And most importantly, every function needs to know the width of the stack frame at compile time.
Well, yeah, it hasn't got anywhere to put that additional information that's in a circle.
Yep, since we've only defined that we take in a shape. So there's no way for it to get the circle members. When circle gets copied into display, only the shape members get copied over. The circle members remain where they are. Which means it's very much impossible for display to work properly when copying shapes in that are not shapes, that are circles or derivatives of shapes. Now, given that the problem is that the display stack frame literally physically does not have enough knowledge at any point in time to make a decision about how wide the stack frame should be, other than to make the stack frame large enough to contain the shape members, but it doesn't have enough knowledge to make the stack frame large enough to contain the circle members or the rectangle members if there was a class called rectangle. What would be a potential solution to this first problem? How can we get display to still think about things in terms of shapes, but allow it to access the memory of a circle? How do we represent this polymorphically?
With a plasticine parrot.
Virtual hasn't come up yet. We're solving this first problem first, as opposed to this first problem second, because that would just be silly. The answer is we use a pointer. Instead of copying this circle into a shape, this is what we're going to do. We're going to turn this display method to take in a shape pointer, and then we're going to pass in the address of this, which means this shape pointer now points to, now this is important, it still points to the bit that makes a shape a shape. It doesn't point to the bits that make a shape a circle, because that would just be ridiculous. It still has to be a shape. But what it's pointing to is the aspect of circle that makes a shape, but it's pointing to it within the context of a circle object.
I know this is slightly bizarre, but it's always stuck with me ever since I first heard Jason say it. It points to the bottom left of the object.
Yeah.
Do you know what I mean? It points to the corner of the object where it starts.
So, does everybody so far understand the first solution to the first problem? That we can now have display, because a pointer is a fixed size, that pointer may point to anything. And that anything is going to include derivatives of the type. How's everybody feeling about this so far?
Shiny, apparently.
Okay, so let's try to fix the program, given our new knowledge. This is now going to take a shape pointer.
Let's try and find the end. You got it on the first try.
You what?
You found the asterisk on the first try.
Oh. Yeah. I am getting better at this with all these symbols. Okay, so again, we're going to have to make some modifications because we're using a different pointer access symbol. And we're also going to have to pass in a reference to, the address of circle. But you'll notice another problem. So display shape is now appropriately pointing to the correct data. Shape is a circle. Watch this. If I debug this right now and look at shape, I get a debugger fail. A miserable debugger fail. Well, whatever. The point is, shape is a circle now. In the context of display shape. No, this doesn't work if shape and circle are the same size. A circle can have as many additional members as it wants to, but when we access it through a shape variable, we get the appropriate shape members. But you'll notice. You what?
The thing that I was just saying, the thing that Nelson said was the same size as the pointer.
Yeah,
that's the key thing, because you'd mentioned that in passing. But because the pointer is the same size, being a pointer and thus always the same size.
Yep. A pointer to a shape is the same size as a pointer to a circle, is the same size as a pointer to arbitrary memory in your computer. So now we have one more problem. Our code still doesn't work. Why doesn't it work? Well, we're pointing at the same object. I mean, although I couldn't prove that given the debugger being lame, we are. Just take that, that's just what we're doing right now. But there's another problem. There's no logic that the C# compiler, the C++ compiler is not emitting any logic that can decide which one of these methods to invoke, whether the method is on line 10 or line 22. And the reason why is very straightforward. If I was going to go ahead and implement a rectangle, and I'm not going to do that because that's going to be an exercise to everybody, but if I was to go ahead and implement a rectangle, I would have a third implementation of get corners and a third implementation of get area. At that point, if we invoke display shape with a rectangle, it invokes rectangles, get corners. And if we invoke display shape on a circle, it will invoke circles, get corners. But we haven't told the C++ compiler that we want this functionality yet. What we need to do is we need to instruct the C++ compiler to create something called the virtual function pointer table. So basically, we have this display function that takes in a shape pointer. However, when we say shape get area, which get area does it load? So let's step back a little bit and talk a little bit about images.
Images?
Yes. PEs, or portable executables, are considered to be images. And when I say image, what I mean is that that's sort of like a term used for what I'm about to describe, in that portable executables get loaded, get mounted into memory. Everything in your executable gets copied from your hard drive into memory. The implication of this is that every bit of executable logic and every function that you've defined and every function that has been generated for you by the compiler and every function that has been imported by includes has a memory location. So, for example, shape get area has an address. And let's say the address is 0x50. Circle get area has an address. Let's say this is 0x70. Every function has an address. In fact, all a function invocation is, well, not all it is, depending on your calling conventions, a few things might happen in addition to this. But at the end of the day, every time you invoke a function, and when I say function, I'm including methods, because at the end of the day, the compiler turns functions into methods anyway. Or, sorry, turns methods into functions anyway. Every time you invoke a method or a function, you are executing a jump statement, essentially. It's a little bit more involved. There is a call operator and so on, and you have to worry about building the stack frame and copying the parameters and all that stuff. But the fact is, at the end of the day, when a function is invoked, execution inside of your code jumps from one location of your portable executable to another location of your portable executable. Which means that we can take advantage of the fact that is everybody good with the idea that at the end of the day, your executable code is simply data that is copied into memory, and every function gets an address? Is everybody good with this? So there's a great thing that we can do in code, and there's a great concept that we can represent. They're called function pointers. We're not going to be talking about real function pointers, and we're not going to be looking at the syntax of function pointers, because the syntax is ridiculously ugly, and they're very limiting. But they're not unlike delegates in C#. A function pointer is a pointer to a function in memory, and you can decide to jump to a particular function based off of any criteria that you wish in your program. We can take advantage of this. What if we were able to tell the C++ compiler that a shape should look like this? A shape should have a get area pointer on it. It should have a get corners pointer on it. So when I say a get area pointer, I'm referring to a pointer that can point to a function that matches the signature of get area. So I want to tell the C++ compiler, for every shape that's instantiated, it should have a get area pointer and a get corners pointer. And when we invoke shape.getArea, I want it to reach in to this pointer, check to see what it's pointing at, and invoke what it's pointing at. Then, every time I instantiate a circle, I want the C++ compiler to essentially do this. I want to say, if I say circle C1, I want the C++ compiler to also inject a new bit of code for us. I want it to say C1 dot get area pointer equals the address of circle get area. Actually, the parentheses wouldn't be there because we're not invoking that method. This syntax is actually kind of close to something you can do in C++, but I'm not intending for this line to be compilable because it truly isn't. But I want every circle and every rectangle and every triangle. I want everything that derives from shape to have a pointer to the getArea function. And whenever I invoke the getArea function via a shape, I want the C++ compiler to inject additional code that will actually look up where this specific object points to when asked for a very specific method. So that by saying circle C1, C1.getArea equals circle getArea, when I say display the address of C1, I want it to invoke this method when the getArea method is invoked. If I say rectangle R1, I want the C++ compiler to inject code that says R1.getArea equals the address of rect getArea. And then when I say invoke display address of R1, I want the display method to invoke this getArea, the rectangles getArea, not the circle getArea. Does everybody understand how this approach would solve the problem that we have had? Because this is a fairly complicated bit of logic to understand, but we truly are treating functions as if they were data. And every object that's a shape has a pointer to the getArea function. And every time we instantiate a derivative of a shape, we want the C++ compiler to automatically assign that pointer to that function. And where it exists,
the relevant,
yeah, where it exists in memory. Because let's say 0x80 is rect getArea. Every function has an address.
While we're waiting for anyone to type questions, I'll get this all out of the way at once. 50, 60, and 70. It's not decimal.
506070?
As opposed to 50, 60, 70.
Oh. Right.
It's alright, I was just saving them all up to do in one go while we were waiting for people to ask questions.
Hey, James. Oh, a wild Jason appears.
Oh,
Ah.
I've been here. Pay attention, boy. I'm sure he's house-trained. Must be by now. What?
What?
What? He said wild Jason.
Oh, yes. Okay.
Ow.
Okay, so if there aren't any more questions, let's talk about what really happens. Like I said, this is a potential solution to the problem polymorphism. What really happens is that every single class that is annotated by the programmer to contain what are called virtual methods will cause the C++ compiler to generate something called a virtual function pointer table. There's one per class. The virtual function pointer table points to every function. So here's like the virtual function pointer table for rectangle. It'll say getArea equals the address of rect getArea. The virtual function pointer table for circle would say, so this is rect. The virtual function pointer table for circle would say getArea equals the address of circle get area. Every circle has a pointer to the virtual function pointer table. So C1, C2, C3, if all of these are circle objects, they all point to this virtual function pointer table. All the rectangles, R1, R2, R3, all point to the rectangle's virtual function pointer table. And no matter what context we operate under these objects with, if we cast or if we convert these objects into shape pointers, accessing the virtual functions will cause a lookup into the virtual function pointer table at the appropriate times.
Which is cool.
So
Can make sense because there's no, there would be no reason to have this, have that done separately for every instance of an object. It's always going to be the same. The area of a rectangle is the area of a rectangle, and that's that.
Okay, I'm going to go ahead and implement this in code real fast and introduce a few new keywords, and then we'll see if people have any more questions. So, how do we tell the C++ compiler that we want something in a virtual function pointer table? Well, logically, we do so at the base level. The reason I say logically is because display shape only knows about shapes. It does not know about circles. In fact, it would not be a compiler error for me to even define circle after display shape. Display shape has no concept of what a circle is. It only knows what a shape is. Therefore, it's logical that in order for the C++ compiler to emit the additional code required to invoke get corners and get area, it will have to be annotated somewhere on the shape itself. We annotate it using the virtual keyword. The virtual keyword indicates that these methods are virtual, and that any invocation of these methods should be deferred to the virtual function pointer table that could be different depending on what object is passed into a particular function. So now if we go ahead and run this code, you'll notice we get the appropriate result. People coming from C++ people coming from C# or Java might be curious as to why I didn't have to annotate the members on line 27, 28, and the fact is you just don't. However, I typically do anyway.
I'm getting so used to the oddities of C++ that it didn't even occur to me that yet. It's disgraceful.
Okay. By annotating these methods with virtual, we have told the C++ compiler to create a virtual function pointer table for every derivative of shape. And we've also told the C++ compiler that whenever we instantiate a circle, we want this to point to circle's virtual function pointer table. And we've also instructed the C++ compiler that whenever we invoke these methods, that it should not invoke the methods that it immediately knows about at a compile time. Instead, it should do something called, that's a process that's called late binding. Which is funny because late binding is actually one of the major components to dynamic typing systems. But this is a form of dynamicism that is present in most static languages, where we can our method invocations are late bound, where the shape get corners, it doesn't know if it's going to a shape, it doesn't know if it's going to a circle, it doesn't know if it's going to a rectangle. Is dynamicism a word?
Mm-hmm.
Oh, I got lucky.
Well done.
Okay.
Spell it.
Okay, how's everybody feeling about virtual function pointer tables, virtual members, public inheritance, member hiding, and using pointers instead of direct objects to reference base types?
Just to clarify, now that you've come to virtual, well, for a start, override isn't a thing that exists.
Yeah.
Yes, it's not.
It's not. It's something that's implied.
Right. And the other thing is hiding. That's something that generally you will not want to be doing.
Ever. You don't even want to be doing it in C#.
No, certainly not.
But C# will say, it's funny the way C# deals with hiding. It'll say, well, I'll still compile, but if you want this
I'm
warning
going
to
to
go,
treat you as if you're stupid.
yeah, if you want this warning to go away, you will have to put the new keyword in. Otherwise, I will complain at you every time you compile. But yeah, member hiding is not fun and not desirable. What was that? Okay. Oh, never mind.
That was me muting in time.
I just got it. Anyway, really, is that it, everyone? Like, I mean, this isn't the end of the class, but we just covered like the most intense.
I'm still not sure whether it's just it's that Friday feeling or this class is ultra elite.
Yeah.
But compare the questions panel. The question panels, no questions essentially.
Yeah.
You just don't seem to make them do a lot of work.
Well, no,
these
I'm
days.
about to, because I really wanted.
Oh, okay.
Because they're gonna have to do some stuff, because obviously they all know it. I just want to stress the fact that Segfault, if you fail at doing any of the assignments during class, I will have to slap you.
You could just slap him anyway on principle.
True. Anyway, this is such important stuff, major important stuff. We're going to be talking we're going to be talking about interfaces pretty soon here. We're going to talk about some design stuff, but first of all, what I want people to go ahead and do is I want people to implement a rectangle class and use it in main in the context of the display function. I mean, I think that should be implied.
And a square class.
Yeah, okay, fine. Let's have them do two things.
Goodness sake. I was almost going to suggest different types of triangles so they could do multiple levels of thing. See, I've always got the feeling that whoever decided on the terminology used in programming, their dictionary, it was like missing a lot of letters. Because there's so many words clumped together around I that all mean slight variations of the same thing. You implement interfaces while you inherit, and you multi-inherit.
It's okay, Gavin. Take a deep breath.
Yeah, what about?
It's just called words.
Okay, go ahead and hit the participate button, everyone. Notice how this time I didn't ask if you wanted to or not. Okay, so I'm going to go ahead and pause the video, and let's see if you guys can go ahead and hammer this code out.
Rah.
And we're back. So let's go ahead and implement a rectangle and a square. How do we implement a rectangle and a square? Well, we type in rectangle, we inherit from shape, and we fail at typing repeatedly. We go ahead and set a set width int width equals width. I want my automatic properties.
You should go through and set up some snippets. Not like in class, I just mean generally.
Yeah. Alright, how many corners does a rectangle have? It has 4. What's the area of a rectangle? Width times height. So that's our new polymorphic shape type called rectangle. And it implements shape, and it overrides the appropriate members, and it annotates shape with some additional data, width and height, respectively. Now, to implement a square, things are just a little bit simpler, because now we don't have a height to worry about. It still has 4 corners, and the algorithm to determine the area is to square the width. So now we have a rectangle, a square, and a circle that can all be used as if they were shapes, which is the most important aspect to understand. So if I say rectangle rect dot set width 10, rect dot set height 5, and then I say display shape address of rect, and now I can do a square dot set width 10, display shape square, and I can go ahead and hit a 5.
Very nice. There is one thing that's slightly worrying, though, to me. What if someone just decides to come along in main and make a shape?
Yeah, that is going to be a small issue. Well, it's not. It's not an issue in that it's going to negatively impact our program. It's an issue because it makes no sense. There currently is no problem with this code.
In terms of code?
Yeah, in terms of code. I'm allowed to instantiate a shape, and I'm allowed to display it, and that doesn't make much sense because a shape's more of an abstract concept than a circle or rectangle or square.
Yeah. I mean, what are you going to display? How many corners does a shape have?
Yeah, we already talked about this earlier when I was like, how many corners does a shape have? Well, it doesn't have any, so I'm going to return 0. What's its area? Well, I don't really know, so I'm going to return 0. That's very poor code. And not only that, it also still allows us to instantiate shapes. Shapes are more of an abstract concept. The reason we have this, the reason we are using inheritance in this particular situation is to be able to write code in terms of an interface.
Bam, bam, bam.
Okay, so let's back up. How can we make it so that both we do not have to how do we make it so both we do not have to provide an implementation for our virtual members when it makes no sense to have an implementation for them? And how can we simultaneously make it impossible for shape to be instantiated? The answer to that question is abstractness. To make a method abstract in C++, it must be virtual, and you delete the body and replace it with equals 0. Now, if anybody thinks that they're clever and does this, I will be very upset. I want to point out that I have seen this being used by people. Really, derp. I'm going to make because null is just a define for 0, right? I'm going to make my virtual members be abstract by saying equals null. It looks kind of exotic, but you know what? It doesn't make any conceptual sense. Equals 0 is how you should perform this bit of logic, and the fact that null.
Well, it makes more conceptual sense to me than 0 does.
It does, but on the same token, null is a value that not only may change between compilers and operating systems, but also is only appropriate for use within the context of a pointer. The equals 0 is the actual C# specification saying that equals 0 indicates abstractness.
Oh, that's a different matter.
Okay, by making this abstract, we have done 2 things. We've accomplished 2 things. Or actually, we've accomplished 3 things. First of all, we've made it so that we no longer have to provide implementations that are pointless to provide in the first place. We've also made it so that shape may not be instantiated. You'll notice that if I try to compile this code, line 65 is an error now. Shape cannot instantiate abstract class. So shape may not be instantiated. The third most important aspect of virtualness is that I am now forced to implement every virtual member within the shape class to create a non-abstract class. What I mean by that is that in Circle, if I was to take away this get corners implementation, like commented out, and then I tried to build, notice how Circle remains valid. Circle is still a valid class, but it becomes an abstract class, and as a result we get an error. object or abstract class type circle is not allowed.
So, and presumably that's there so that you could then have something, some sort of more specific than a circle that inherits from circle that would have a...
Right, that would have a getCorners method.
Right, cool. And you can do all this, I mean, patently you can, because it's not complaining about this specifically, but you don't need to make the class abstract, the shape class.
Abstractness in C++ is implicit. It's implied by the existence of one or more abstract members.
So there isn't an actual abstract keyword?
No. You'll notice that says, error, this declaration has no storage class or type specifier, which is C++'s very obscure way in saying, don't use it here.
You'll notice that, oh yes, we're in C++.
So yeah, the abstractness of a class is determined by the existence of one or more abstract members. Another term for abstract members in C++ is called pure virtual. So if you ever hear pure virtual, that is just a synonym for abstract. So getCorners in the type circle is pure virtual because we don't provide an implementation. Yeah, you may only have virtual methods. In fact, that's true of every language. Now, you might be saying, Nelson, well, you can have virtual properties in C#, and then, what are properties again? Properties are just methods.
Yeah.
It doesn't make sense to have anything other than methods be virtual or abstract. So there's the only two things that you can, or the only things that you can make an abstract.
Although by that reckoning, I still maintain it doesn't make any sense to have private and public types of intent anyway.
Okay, so that's great. Shape is now an abstract type. But shape is, there's something more important about shape now. Very important about shape, and this brings us into a small discussion about some design considerations and some of the terminology we use when discussing these designs. In many languages, there's such a thing as an interface. Now, you'll notice I use the word interface quite frequently, even in contexts that don't describe the interface keyword. For example, I could correctly say that all of these public methods under rectangle is rectangle's public interface. But that's a different word with a different connotation. When I say shape is an interface, what I'm saying is that shape defines a shared bit of functionality that must be present in any class that inherits from it. But the result of that is that you may safely use any shape in any way that you wish and fill it at runtime with different implementations. So this display shape function is polymorphic because it takes in a polymorphic type. Shape is a polymorphic type in that it provides virtual members. So shape is an interface, and it's an interface because it is an abstract class that only has pure virtual methods. That is the definition of an interface. Now, like I said, unlike other languages where you have an actual interface construct, like Java or C#, where by using an interface you constrain yourself to this constraint, whereas in C++, by following this constraint, you represent this idea. So shape is an interface in this case. And an interface should only ever have public, pure virtual, public or well, it doesn't make any sense to have protected, anything that's protected, and it especially makes no sense to have anything that's private. That's just completely ridiculous. But an interface is going to always be something that has public, pure virtual methods in it, and that's it.
So if getCorners in your shape class actually had some implementation.
Yep, it would no longer conceptually be an interface. It would be an abstract class.
It sounds to me like the idea of interfaces exists in C++ more than actual interfaces do.
Exactly. It's just like how you can. This is slightly a contrived example, but you guys are all familiar with the fact that you can shoehorn C into writing object-oriented code. And in C++, you don't have an actual interface construct, but you can represent the idea of an interface. And it is useful not only to conceptualize types that have only pure virtual methods as interfaces, but it's also useful to annotate them as such. So the annotation that you'll typically apply to any class that follows the definition of an interface is prefixing the type with the letter I. So by prefixing it with the letter I, we'll get a bunch of compiler errors because now every instance of shape is invalid. So let me go ahead and fix all these references to the old name. And our code compiles and does the exact same thing it did before. The difference being is that we have clearly annotated that shape should be treated as an interface. We've also clearly annotated to any other programmer down the line that it is inappropriate to add any implementation to this type, because in adding implementation to this type, it's no longer an interface. Okay, cool. So how's everybody feeling about that so far?
There's a couple more questions coming in.
What's the syntax to raise to a certain power? It's multiplication repeatedly. There are built-in mathematic functions, but there's quite a few of them, and I'm not going to be talking about the math functions yet. But to raise something to a power, you would just repeatedly multiply it by something. The syntax that you might assume would do that is actually the XOR operator. Does I of shape really change something, or is it just a name thing? It's really just
a
name thing, but it's an important name thing. It's important because it indicates to yourself and other developers that this type should be treated as an interface. It should never have any implementation inside of it. And we're going to be talking a little bit more about that concept once we start talking about multi-inheritance. Could you overload display shape with, say, circle pointer circle or rect pointer rect, even though it's more complicated? Now, you certainly could. But by doing this, we have, in effect, caused a compiler error because rectangle isn't defined yet. We've, in effect, defeated the purpose of polymorphism entirely. Now, sometimes it's desirable to do this, I suppose. I'm not going to say that, never ever do that. I'm just saying if you find yourself doing that, you might want to think about your interface, and you might want to decide to refactor your interface slightly so that you're not forced to repeatedly add additional implementations of particular functions. So I would not... Again, I'm not going to say that this isn't useful. This isn't bad, nor is it good. It's just a thing you can do. But it could be an indication that your interface is poorly designed if you really need this special functionality so often. Okay. So let's talk about multi-inheritance.
I was sorry, before you go on, I was just pondering that question. Presumably that would be something you would be more likely to do if this was a one-hit thing. You would just for this sort of one part of your program, you were dealing with shapes and nowhere else, and it was never going to be used again. Hello?
Hello?
Nelson?
Yeah.
Presumably that's the sort of circumstance really where you would actually overload instead.
Yeah, if it gets complicated, it really does. If the custom functionality that I would want to change within the overloaded member is something that I could get away with representing in the interface definition itself very easily, then I would do it in the interface itself. However, if I did need a little bit of custom functionality for a particular polymorphic type, I would use a dynamic cast, which is something that we're going to be talking about very soon, actually.
So, dynamic code.
Well, actually, let's talk about multi-inheritance, and let's talk about polymorphism in a way that is actually considerably more useful than what we have represented at the moment. Okay, let's go ahead and create another interface. The iGame object interface will have a public int getID member. That'll be virtual, because everything needs to be virtual. It's an interface. It'll also have a virtual void update member, which will be, again, pure virtual. So the iGame object is going to represent all our game objects in our engine. And the great thing about this is by making this an interface, we can now write an engine class. And let's bring in our vector. We can bring in an engine class, create, let's say, a vector of iGame object. Now, look at this. If I were to complete this like this, and say game objects, what's going to happen?
And why?
You know polymorphism? You polymorphism know? No, you polymorphism. Polymorphism know you.
I was looking at that even before the no came in. You polymorphism. He's calling you a polymorphism. I wouldn't stand for that. Okay. Would you like to rephrase that, Rolling Stone? Because genuinely, I have no clue what
Oh, this is going to be great. So we get an error that says iGame object cannot instantiate abstract class. Which actually, here's the funny thing about this error. That's actually a nicely written error. That, while a little bit roundabout in its wording, indicates to us the problem. But never double-click on the error, because you'll end up inside of...
It seems to be on line 869. Ah, yes.
Yeah, it's actually inside of... The error happens inside of the vector type. Because of how templates work. So, instantiating an abstract class doesn't make any sense. Containing a vector of abstract classes makes even no sense more. Even makes more...
Even what?
Just like that sentence.
Yeah, that's exactly
absolutely
the
no
thought,
sense more.
That's the exact thought process that the C++ compiler goes around when trying to reconcile what you told it to do. Because it doesn't make any sense. It's an abstract type. You can't have an instantiation of abstract type, and you cannot use a collection type with an abstract type. That's impossible.
But what can we do instead?
Well, exactly. What we do instead is we point to it.
We do.
So now we have the game objects, and I'm going to go ahead and add a method called add that takes an iGame object pointer, and adds it to our game object. Game objects, push back, game object. And then we can have a void. Let's call this this function
Gerald.
Oh.
Let's say game loop. And the game loop is going to say, while true, it's going to be infinite for now, I want to do two things. I want to update, and then I want to render. Now, update and render haven't been implemented yet, so I'm going to go ahead and implement them. I'm going to implement these privately, because the only reason I have these methods here is as a convenience to myself.
Just to separate your code out. Question mark. Hello?
Hello?
Hello.
Just to separate your code out.
Yeah. Make the code a little bit cleaner. Okay, so let's talk about this code. We update and then we render for every frame of our game loop. Actually, you know what? I'm not I just realized that I'm thinking ahead to how I'm going to use this example. I'm going to make update and render public and get rid of the game loop. I'm going to have the game loop inside of main, and you'll see why soon. Okay, so the update method loops through all of our game objects and updates them. And the render method, here's the functionality that we want to express. We want to say, if the object we're looking at is a shape, print out its area. Well, how do we do that?
So this is the equivalent of the as operator in C#.
Yes. This is a situation when we will choose the runtime behavior of our code depending on the actual implementation of whatever object we're looking at through the eyes of a more abstract concept. So although we have a vector of iGame object pointers, some of those game objects may also be shapes, and our engine knows how to render shapes. So what it's going to do is it's going to say, okay, C++, try to turn this into a shape. Check to see if that's possible. If it is possible, give me back a shape pointer. If it is not possible, return null. In which case, if that's not possible, line 36 is true, and I continue the loop without rendering the shape.
Lovely.
So how's everybody feeling about the implementation here with this particular code?
Positively fraptious.
Sweet. So what I'm going to go ahead and do is I'm going to have my rectangles and my squares and my circles implement iGame object. What I've just done is shown an example of multi-inheritance. In C++, you can inherit from as many classes as you wish. But there are some major considerations to take into account. When you combine multiple classes, and those different classes have functionality built into them, have implementation details, and potentially those different classes have conflicting names, you'll result in a very, very difficult to reason about program. As a result, the recommended way, the basic principle of multi-inheritance in C++ is that you may implement as many you may inherit from as many interface classes as you wish, but you should only ever inherit from a class that is not an interface once. So if
you should only. You're saying you should only.
You should only inherit from one non-interface type.
Right.
But you can inherit from as many interface types as you wish to represent the code. So let's go ahead and implement the members of iGame object. We have this int getID member, which I'm not going to worry about. I'm just going to say return 0. And then we have a void update method. The void update method, I'm going to go ahead and, well, first of all, I'm going to make these virtual. The void update method, I'm just going to say width minus equals 10. Every time we update a rectangle, it gets smaller by 10. So I'm going to do the same thing to square. I'm going to say square. I'm going to bring over these implementation details, because otherwise the code won't compile unless I implement these, because it would turn square into an abstract type, because I need to implement everything from my game object. And I'm going to say width minus equals 5. Then we do the same thing with circle. I'm going to make the radius, I don't know what I'm going to do. I'm going to add 2 to it on every iteration of the game loop. Then I'm going to go ahead and add a player class that is not a shape. I'm going to implement the game object members for it. And inside the update method, I'm going to say, I don't know,
Cuthbert, Dibble, and Grub.
Doesn't really matter what I put in there. Okay, so I'm going to do a rectangle R1, R2, squares S1, circle C1, C2, and player P1. Say R1 set width 100, R1 dot set height 30, blah 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 blah. This is gonna be fun. Set width blah 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 set height, blah, 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 S1 dot set width 490, C1 set radius 4, C2 set radius 10, and now I'm going to add these into my engine. I'm going to create an engine, and I'm going to say engine.add R1, R2, S1, C1, C2, P1. Then I'm going to enter an infinite loop, and I'm going to say engine.update, engine.render, and then cout, press or hit enter, and then cin.get. So now when I run this code, we'll see we get some compiler errors. And the reason we get a compiler error is I defined iShape below where I defined engine.
You managed to make it sound almost as though you meant to do that.
Yeah, of course I did. Okay, so we see our player updating, and then we get all the rendering of the shapes. And when I hit enter, notice how the shapes actually change, because I'm updating them on every iteration. But the rendering is handled from the engine, and it takes advantage of the abstract members provided in the iShape interface.
Very nice. So, any questions about that, really?
Particularly about how the engine's implemented, how we're using polymorphism, and we're performing different logic depending on what behind the scenes a particular object is. Using the
does
dynamic
everyone
cast.
get what's going on between lines 42 and 44? Speak now or forever hold your pieces.
Yes, I polymorphismed. I polymorphismed considerable amount of times in this code. I can't think of anything more to talk about. I mean, we've talked about, what we have covered today is we've talked about inheritance. We talked about a basic level of creating additional classes that bring with them the implementation of other classes. But inheritance in itself isn't as useful as you might think it would be. Inheritance really starts to become useful when we introduce the concept of polymorphism. We do so with the virtual keyword. The virtual keyword provides us the facilities to change the implementation of a particular function, not at compile time, but at runtime. And it provides us a lot of flexibility in regards to that. Then we defined what an interface is. Although C++ technically doesn't have interfaces, we can get away with calling these things interfaces. And it's useful to think of them as interfaces. I know a person earlier said something about that, how is this just a naming convention or does it modify the behavior? Well, keep in mind that you should never implement from more than one non-interface type. You should never inherit from more than one non-interface type. So by delineating your interface types from non-interface types, you make it a lot more easy for you as a developer or for other developers on your team to be able to know for certain whether or not the author had intended that type to be considered an interface or an abstract class.
Presumably this is why when they came to design C#, they locked this behavior down.
Yeah. They realized that people were doing this anyway, and they made this actually the only way you can do it. In both C++ or C# and in Java, you may only ever inherit from a single type, but you can implement from multiple types.
Mr. Heathcote asks a question.
Why is it useful to be able to cast when you don't know if the cast will succeed or not? Is that bad design? Well, not necessarily. I'm querying the object. I'm saying, hey you, do you do this? The object's either going to say yes or no. And if he says yes, what I get back is a statically typed local variable that will allow me to invoke the functionality using the rules or constrained by the rules of the C++ programming language.
The key point being, it's not that we don't know if the cast will succeed or not. The key point is that we are dealing with the situation where it fails, and we're dealing with the situation where it succeeds. We're dealing with all the outcomes that are possible.
Exactly. If
It would be a design problem if we weren't sure whether it would succeed or not. You know, if line 43 and 44 wasn't there,
yeah,
line 42 would be of no use to you.
basically what's going to happen now is we'll get an exception, because shape will be null in the case of a player. So this is all about querying the object at runtime to see if it supports a subset of functionality. C++, remember, is a statically typed language, and doing this sort of thing isn't necessarily something you often do in dynamic languages. In dynamic languages, you don't do this as often. You're not forced to think of what can go wrong with your objects, and as a result, there's a lot more room for making mistakes. In C++, when you want to cast something, you must be explicit, unless that cast can work 100% of the time. A conversion from a square to a shape will succeed 100% of the time, because a square is a shape. A conversion from a shape to a square will only succeed in certain scenarios when the shape actually is a square, and it will fail other times. As a result, the C++ compiler enforces that we're explicit when casting from a base type to a derived type.
So has that made that a bit clearer for you? I'm assuming that you're either Thierry Dan or Zolkos, and that it does indeed make sense.
Okay, because I've run out of things to talk about, I'm going to go ahead and hit pause and go on the last break for the night. And I encourage people to ask questions and see if anybody isn't
About anything we've covered at all, really. And if there's something that you're not clear on that we've covered in the course, now is your chance to.
Yeah, I mean, the goal was...
Yeah, because
ask about it,
because after this we're about to take a 2-week break before 102 starts.
Yeah, and most importantly, people hopefully went from finding out what a variable is to finding out at least the concept of a class, and hopefully has an idea of polymorphism, because that's going to spearhead us directly into the next course when we will be using these tools to actually create applications that are more than just toys. Well, we haven't talked about metaprogramming yet, so they're not advanced enough. Okay.
Not advanced enough, yeah, exactly. Come on, Segfault.
You mean Meta's a bot?
Well, yeah.
I thought she was real.
No, she's down for maintenance for the weekend.
Is that what the kids call it nowadays?
Yes, they do.
Sorry.
I'm going to go ahead and hit pause and stuff. And we're back. So, question on memory order. Is the base class positioned first in memory, followed by the derived? I do not know the answer to that question, but I would assume that it is. I don't know if that's simply an implementation detail of how a compiler decides to lay out your memory, or if that's a detail of how the runtime decides to lay out your memory. But logically, it makes sense that the members that are from the base type would appear first, so that you can operate on that base type or via a base type pointer and be able to constantly reference the members of that type without having to know what may lay beyond from the base type.
As this kind of very brief sidebar to that, is there any way of sort of directly auditing the virtual function pointer table?
Not really. There is like for example, if I put a breakpoint right here, and if I inspect a game object pointer, you'll notice that there is a VFPTR, virtual function pointer table, and you'll notice that if I expand it, it does give me what the actual members are. Because this is a rectangle, therefore the virtual function pointer table looks at these members. But other than that, there's really no way to audit that.
Okay.
So the engine's update method calls the update for any type passed into it as iGame object. Yes, the update method loops through all of the game objects and invokes their update method. You'll notice that our iGame object interface provides an update method that is a requirement to any type that derives from iGame object. About interfaces. It basically is a blueprint for other classes, and any class that inherits from it must use any method on it. Well, yeah, it is a sort of a blueprint. It's an interface.
It would be more of a contract if it made you do it, like it should.
Well, yeah. But think about like an interface. Think about like USB, for example. You have a phone and you have a computer. You really can't take your phone and shove it in your computer. Nothing in your phone would connect to anything in your computer unless somebody came up with an interface. And they did. It's called USB. So you use that common interface to communicate between two different pieces of technology. They both are forced to, because they both understand USB, they're both forced to follow the USB specification. But if they do, they can communicate with each other. And so when you cast the base class, the size of the object is the size of the base class, and when you cast it to the size of the object is now the base size plus derived size. You may not upcast without pointers. You can't go from a non-pointered shape to a non-pointered rectangle, because that doesn't make any sense. The rectangle won't have enough information to be a proper rectangle. So you
I imagine that's probably referring to where you've done the, what I should insist on thinking of as the as operation.
Well, in this case, we're upcasting, we're downcasting, but we're downcasting via pointers, meaning that a shape pointer is the same size as a game object pointer because they're both pointers, so they don't need any additional information. Now, of course, how much information is actually allocated for the type that's being pointed to may be different, but that's the nature of pointers. We can point to anything. Is the project for C# 103 a roguelike? These words do not make sense to me.
No.
Is 102 going to have Windows-based coding, or are we still exploring console applications? We are going to be working in the console. Once we start talking about the simple fact is, once you want to get to actually representing something graphically, you have a variety of options. You can go with OpenGL, or maybe you can go with a wrapper around OpenGL, such as Glut or SDL. Or you can go with DirectX, or you can go with HTML with the new Windows Runtime for Metro-based apps. Or you could go with Win32, which you really shouldn't. Or you can go with MFC, which you also really shouldn't. Or you can go with Qt or WX widgets or whatever. And the point is once you understand C++ at a general level, understanding how to use a particular library to get a particular result represented to you graphically is going to be more or less an exercise of reading the documentation. That's not to say that we are never going to be talking about that stuff. We certainly are. But the fact is, I want to stay agnostic of what API we'll be using for rendering as much as possible so that we can explore the concepts of C++ that are inherent no matter what type of development you inevitably do with it.
Yeah, it becomes splintered once you start talking about.
Yeah, because then we also exclude a bunch of people. Because if we do a DirectX class to explain a bit of C++ that's actually applicable to both DirectX and OpenGL, a bunch of people will be like, "Oh, we don't want to, do the DirectX class. We want an OpenGL class," and then they won't attend. When in reality, we still have plenty to talk about that has nothing to do with what eventual API you use.
Although I would like, I think it's good that you asked that question and gave us a chance to answer it, because I'm surprised it hasn't come up more in the programming classes so far. Because it's a traditional forum perennial, you know. How long before we get to doing graphics stuff?
Right.
That whole, the console's boring.
My answer to that is slightly facetious, but you're ready to do graphic stuff when you can pop open the documentation and understand it enough to get a result. Because that's all it truly is. But like I said before, there's so much more to talk about than a specific API. I don't want to bog down our discussions about general C++ coding with discussions about the quirks and the processes and the concepts of using a very specific API.
Plus, you start to need to know some proper maths.
Yeah.
Before you deal with graphics.
What would be the best for a game? DirectX, OpenGL, or SDL?
Yes.
Yes. If you can actually answer that in a way that is... If you can choose any one of those technologies and make a convincing argument that 100% of the time that argument is true, I will give you $1,000. Because there truly is no... each one of those technologies that you listed, DirectX, OpenGL, and SDL, well, SDL is built off of OpenGL, by the way. They all have different implications. DirectX is obviously going to be Windows only or Xbox 360 only, and OpenGL is going to be obviously cross-platform. SDL is obviously going to be tailored towards two-dimensional games using OpenGL, and depending on what it is you're trying to bring to market, it really depends.
Sheep.
Sheep?
To market. I decided to take sheep to market.
Sheep to market. That's not an appropriate English accent pronunciation. That's more like a... What sort of accent would cause somebody to say sheep instead of ship?
What?
I don't know.
I didn't intend to say ship.
So you said sheep.
I did. I intended to say sheep, so I did say sheep. It's something we do in the English-speaking world. So, as you'll have gathered, we are down to... We've run out of questions.
We did have actually one that I did kind of miss. Sorry about that. Is there a timer function in C++? That gets complicated. If you want to use a timer in C++, you're typically... I mean, you could get away with using the built-in timing functionality to get the current time, the stuff provided by the C standard library. But you would typically really want to use a high-performance timer. And C++, the specification of C++, to my knowledge, 90% certain about this, does not specify the existence of a high-performance timer, meaning that you would be stuck with using the high-performance timers provided by your platform, your operating system's API.
What you're skirting around is the sort of things where you want to be doing this and the situations you want to be using it in are probably situations that are like the update loop.
Yeah.
Where you're really going to struggle for performance.
And you're really going to want to be very precise. So you're going to want to use a high-performance timer or high-precision timer. And Windows does provide a high-precision timer, but that's not part of the C++ specification.
Do you want to show them how to get at it?
The code is so nasty. It's going to be something like this. The query performance frequency and the query performance counter methods, if you looked either of these up on MSDN, you'll get a description of high-performance timing. But it gets a little gnarly, as you can see. right. Is that it?
Somebody did ask quite a long time ago, which is, does virtual work for primitives? Primitive types.
Primitive types don't have methods. Or you're talking about fields?
I don't know, this was quite a long time ago, that question. It just got skipped in the rush, and I found it.
You may not use virtual with fields. That is nonsensical. Am I going to be covering MFC in 102? No, I don't think I am. We're probably going to be focusing more on ActiveX. And writing Internet Explorer 6 add-ins using ActiveX and ATL. And to anybody who thought that was being serious, I'm not. We're not touching ActiveX, ATL, or MFC.
I'm laughing on the inside.
Okay, so is that it? Because we're about to hit the stop button.
Well, congratulations to all the people who made it through this.
Yeah. There's very few of you left.
Yeah.
I'm really proud. The hardcore people stuck in there to the bitter end.
Absolutely.
Thanks, Steve. Nelson's done an incredible job.
Indeed.
And Gavin's been awesome as a powerful little sidekick, always there to make fun of Nelson when required. I mean, it's
You
fantastic.
make me sound like Scrappy Doo, that's... But yeah,
I can't wait till 102 kicks off. That's where things are going to get interesting. So we're going to dwindle this class down by half, I'm sure. No, let's hope not.
No, these guys are they're in for the long haul. They're gonna know everything.
I mean, we're going to get to a point where we're going to be providing content that's way beyond what you get from your typical four-year college degree in computer science with C++ and with C#. We're not planning on stopping. Hells no. One more and I think I'll actually get it.
Excellent.
No, just the big thing is, take this break that's coming up, this next 2 weeks, and continue practicing with this stuff. The more you work with it, the more you practice, the more you force yourself to think logically, the more this stuff just sinks in and becomes second nature.
Well,
like Sekthal just said, code stuff, man, code stuff. That's right.
And really, it's not a case of having to force yourself to go stuff. You know, this is coding. This is what you do. It's typing and then correcting and then typing and then more correcting.
And then failing, realizing your mistakes and making it better.
No, that's just you.
Or just beating your head off the desk repeatedly until you can find out exactly what to Google to find the person who's made it work before. But this is it. So you should start looking at everything, going, oh, I could code an app to do that. Next time like I said, next time you find yourself doing something dull and repetitive with your computer, just take 10 seconds and think, do I know enough to make that? Because the answer is probably yes, with a bit of digging and Googling. And MSDN is your friend. It just pretends it isn't. So yeah, there we go. Right. My obligatory weekly Friday night philosophy lecture is concluded.
All right, well, let's go ahead and stop the recording real quick.
Alrighty. So to all the future viewers of this
video,
all the future people,
thank you.
I'm typing. Cloudy bing bong. Yeah. That's how they talk in the future.
Okay.
Oh, I see.
Well, I hope the future is brighter than it is today. All right.
It's probably orange.
Okay, so goodbye, everyone.